Hello everybody, my name is Soborno. I was here in Very Science Lab. You saw absolutely nothing there. So, there was nothing that happened there. Absolutely nothing, no. So, today, we will be doing trigonometry. Yay. So, I've been looking forward to getting to this part of geometry for a very long time. And it actually marks a big milestone for us, because that means we're about halfway in learning about our geometry journey. So, anyway, we have all the angles of this triangle. That one is 90. That one is 62. That one is 28. But now, what is our problem? Well, our problem is how, so let me type this. How do we find the sides of the triangle? You really gotta love this having no limit. So, anyway, find. So, find there. Find there. Alright. So, now let's actually get to it. So, how do we find the side of the triangle from here? Well, we can actually do it decently easily. So, what we can do is, well, you might be saying, we can just do it in 3 easy steps. Number 1, take the select tool and, that's not what I meant to do. So take the select tool, click on a side. Number 2, click label. Huh? No. I'm not going to do that, because what we're actually going to do is find the sides of a triangle using math. But how do we use math to find the sides of a triangle when we only have the angles? I mean, it's pretty obvious that the largest side is this. This is the second largest side. This is the third largest side. But and we have some idea about the quantities largeness in relation to each other because of the angles. But we actually have no idea about what these actually are. And now, let me present these two puzzles to you. Number uno, we have 2 angles, and this is essentially 3 angles, because we know that this one must be 37 from 1953. So, we have one side as well. So, that's confusing as well. And then, finally, we have that. A right triangle with the sides 5, 12, and 13. You don't know how long that took me to perfect. And this is what we're going to try and do today. How do we find the sides of a triangle from its angles and vice versa? So that's exactly the point of trigonometry. So, anyway, sides from angles and angles from sides. So this is actually kinda easy. There are actually 3 functions. There are more than 3 actually. So there are actually 3 functions. This, that, and that. And there are actually some other functions that I'm not going to include for now because they're a later part. So these ones we're just going to quietly ignore and put a skeleton in our closet. It's not like I don't have a skeleton in my boiler room already. And now, what does SO stand for? Well, SO stands for sine theta, opposite, and hypotenuse. So now, this means that sine theta, well, let's get a better understanding of it using something you might not expect. Circle! No, that's not a very good circle. It's good enough if we just remove this and reconstruct that. Good enough. So now, no, not straight. No, not straight enough. There. Not long enough. Alright, so here is our unit circle. So menacing, threatening. So what are we doing with this unit circle? Well, since it's a unit circle, that means it has a radius of 1. So if you draw a line like this one, it's always going to have a length of 1. But look more closely. Let's use coordinates that are not our regular graph coordinates. So we have a 1 over here, but then we go down from this point. What could that mean? Well, that's one of the legs, y and x. So let's say theta is what we have over here. So 1 is usually denoted as r for radius, though when you're in the unit circle, it's always 1 because it's a unit circle. So that means that you have x and y, and you will also sometimes see depictions of this as so like this. You will also, I'm just going to copy, paste, done. So you may also see it being denoted like this. It's commonly denoted like this because, okay, that's weird. Why is it thinner than everything else I write? Anyway, what I'm going to do now is I'm going to erase this, and this can be called H for hypotenuse. Usually the long side on a right triangle is always a hypotenuse. Then we have Y, which is opposite because it's the side opposite to the angle we're studying. So O for opposite. Then X over here is adjacent to the angle and not the hypotenuse. So A for adjacent. So you will often see sine or cosine or these sorts of coordinates on the unit circle. Now, if I do it on Desmos, it would probably be a bit clearer. So, Desmos, and I'm just going to let Desmos swallow up the screen for right now. So, if we have x squared plus y squared, no, x squared plus y squared equals 1. Alright, so here's our beautiful unit circle in all its glory. Now you may notice it intersects the y-axis and stuff at these 4 points. So 1, 0, 0, 1, negative 1, 0, 0, negative 1. These are the special cases that you'll sort of need to remember. But now, let's say we take x, because that's at a 45-degree angle if you do the math. And now let's see where these intersect. 0.7071, 0.07071. Wait a second. Look at this before you go, what is this guy doing? Root 2, yeah, it's that. And now, divide by 2. 0.7071? Huh, sounds a little suspicious, am I right? So, this is actually a common theme everywhere on all 4 quadrants. So, let's actually draw this. Yoink. Okay, so over here is 1, 0. So this is also interpreted as meaning that if you take what this is, which is 0 degrees, so this is a 0-degree angle, then that means that you're essentially looking at the cosine and the sine of the angle. So since this point is 0 degrees from like the center, that means that that means that cosine, which is the x coordinate, cosine 0 is 1. And cosine and sine 0 also 1. No, it's not also 1. It's 0. What am I doing? So, that's just 0 degrees though. What if we take, say, 30 degrees? Well, 30 degrees would look, maybe the best place for this would be Desmos geometry, but there's no turning back now. So, anyway, how can we do this? So, how can I draw a 30-degree angle? If this is 45 and the slope is essentially 1, and this slope is infinity, then what can I do? Well, this slope is 0, this slope is 1. I think I know what to do. So, now this is 45 degrees. And so, that means that its coordinates, which are 0.7071, 0.7071, which are also root 2 over 2 and root 2 over 2. These are cosine of root 2 and sine of root 2. And finally, one last thing I wanted you to note, this same pattern repeats for everything. Everything. So, if you have 30 over here, So this is a 30-degree angle. This is going to give you square root of 2 over 3, if I am correct, then square root of 2 over 1. Alright, so that is if I am correct or if I am remembering correctly. So don't fully trust me on that one. Bang. Alright, so we've learned enough about this unit circle. Hibber, jabber, blabber, crabber. So let's get to the real stuff. No, that's not the real stuff. Okay. So, what are we going to do? Well, if you take, now we know what O8, A8, and OA mean. Opposite hypotenuse, adjacent hypotenuse, opposite, adjacent. These are just abbreviations, so-called TOA. They don't really mean anything. So, sine theta is defined as being opposite over hypotenuse. Cosine theta is defined as being adjacent over hypotenuse. And tangent theta is defined as being O over A. Or, in other words, what it's essentially doing is it's taking, so what it's, in other words, what it's essentially doing is it's taking O over H and H over A, which is cosine inverse, and multiplying them together. So, this is how we use trigonometric functions. So now, let's use them to clear out that whole triangle issue. So, we have this. How do we solve this first one on the top? So, the hypotenuse is 5. We have two angles, well, essentially 3, as I said at the beginning, because mystery angle strategy. And then we also have this right triangle with no angles except that one that makes it right, obviously. So, anyway, how do we find the sides of this one? The one with the 5 hypotenuse? Well, it's actually pretty simple. What we do is, first of all, 53, so we are going to use this angle in order to find these two sides. So, we can use so to find this side because it's the opposite. We could use ka to find this side, or we could use toa to find both the unknowns. But since toa had no known components in it, then we can't solve it, leaving it essentially unknown for the time. So either so or ka, or we could go through so and then toa. Okay, so I'll do personally ka because it sounds better, and I like the letter A more than I like the letter O. So, even though A only appears once in my name and O appears like thrice. I'm not going to think about that. So, anyway, cosine theta is adjacent, which is going to be the one next, and that's not the hypotenuse, over hypotenuse, the one that is the hypotenuse, which is 5. We know what theta is. It's 53. So now we're left with 5 cosine 53. And from there, it's usually the job of your calculator to do stuff. Though you will be asked to memorize some basic sines or cosines from time to time. But if you have like miscellaneous angles like 53, it's usually not the job of you, it's more the job of your calculator. So, anyway, this will give us, this will actually give us 4 or something close to 4 done correctly. And now, since we have 4 and 5, then we can actually, no, it shouldn't give us 4. I think this should actually give us 3, my mistake. So now, if we take 3 squared plus this side squared is equal to 5 squared, and then we do the math, then we get that unknown side being 4. So we have found all of the sides, seemingly impossibly. But now we have a bigger fish to deal with. What do I mean? Well, let's look at the problem below. So, I'm just going to erase everything here except the necessary parts. Now, let's get us started. 5, 12, 13. We already know all of the sides off the start, but we know none of the angles, besides this 90, of course. But what is that going to do? So, what can we do here? Well, there's actually inverse functions that I never told you about. How dare I? They're essentially just the inverse of our regular functions. So, of course, so is going to be so. Ka is going to be cha. And toa is going to become tau. So, these are our inverse functions. A good way to understand them would be like functions that undo each other. So like f of x being the square root of x, then g of x being x squared. And if you apply both of them to a single, if you apply f of g of x to something, then it's just going to be x. Just like if you apply sine inverse of something, then it's going to give you the original. Alright, good. So now we understand what to do. So how do we do this? Well, it's actually pretty easy. What we're intended to do is actually use the normal so, ka, toa. So, ka, toa. So now, if we take 5, for example, let's say that's our target, and then we want this angle over here. So let's say this is theta, or our target. So we could use any of the 3. I'm personally going to go for ka, because of the reasons I've stated before. So anyway, cosine theta will be equal to adjacent, which is 12, divided by opposite, which divided by hypotenuse, which is 13. So what do we do now? Well, we take theta is cosine inverse of 12 over 13. And that actually I may need the calculator for. So if there's a calculator here, then wait a second, I've got an, oh, this is actually, hey, what? It's displaying some static on my screen, so I'm going to try switching one of the batteries out and putting it back in. These are the right terminals. Okay, yeah, they are. Bang. Why can't I turn it on? Yeah, no, this calculator isn't functional. So instead, what I'm going to do is, first I'm going to lay its coffin. I'm sorry, you were a very good calculator. And second, I'm going to, I could always do this. So let's keep track that theta is cosine -1 of 12 over 13. Keep that in mind, okay? Alright, now we need Desmo's scientific calculator. Calculator scientific. Alright, so I hope you've kept in mind that we have cosine, let me see, cosine inverse of 12 over 13. 22.6. Alright. It's good to know. Cancel. So, this means that we have 22 over, or 23 over here. And with that, we can tell that the last angle is going to be 67. Alright, so that's it. Thank you everybody for watching, and we'll see you next time.